here we are. We're going to go ahead and do an introduction to limits. And I think this is everyone's favorite section from calculus. Not really. It's usually the one that everyone struggles with. But honestly, it all comes back to this same thing we're going to talk about right now. This is the foundation of limits. Every limit question comes back to this same thing. So if you get this down, the rest of limits should not be that bad. I know it's going to be a bunch of crazy algebra, but in the end, once again, this is limits right here, what we're going to talk about right now. This is what we're going to be carrying for the next 9-10 weeks is this very idea. Well, maybe not 9-10 weeks. I have to look at the calendar. But for the next however long we're doing limits for, which is a good portion of time, this is the big idea. And this idea doesn't change. So what is a limit? So there's a new notation we're going to see. But let's read this part right here. Limit is the value that a function or sequence approaches. So the key word here is what value, and it's the output value. A limit is the output value that a function approaches as the input value approaches some value. So basically, we're not concerned with what the function equals. We're concerned with what it's approaching. Now, a lot of times what it's approaching is what it equals, which makes the algebra very simple. But not always, and that's what we're going to see in this lesson is really to focus in on we care about what this function is approaching, not what it equals. So how does this look in limit notation? Well, let's look up here. This is how it looks. This says LIM for limit, the limit of f of x as x approaches a. Now remember, x is the input. So x is approaching something here. So as x is approaching a, as x is approaching some number, what is our output approaching? That's going to be our answer. Our answer is going to be what the output value is getting close to. I like how they say that right here. What is the y value getting closer to? That's basically what you should be asking yourself. As x is approaching something along the x-axis, what's your y value getting close to? That's really what you should be asking. So let's take a look at the graph here. So we have the limit as x approaches 3 of f of x. We're going to find what it equals. So here's our graph. It's defined everywhere except for when x is 3. Now notice they put a hole in the graph. This is called a removable discontinuity. We'll talk more about that later. But it's basically this function exists everywhere, but right here at this particular point, it doesn't exist. It exists for all values. 2.999 would be like right there. 2.999999999 is like right there. So all the values really close to 3 exist, just not at that particular spot of 3, not right here when x is 3. At that spot, our function doesn't exist. It should be -4, but it's not. It's been removed. But right now, we're focused on what's the limit. So we don't care what it equals. It doesn't equal anything there because there's a hole in the graph right there. It doesn't equal anything. But we care what is it approaching. So what's it getting close to? So we have to check both sides for limits. If it's not approaching the same value from both sides, it fails. It does not exist. The limit does not exist. So let's take a look. So here's where x is 3. Let me mark it in red. So right there is where we're looking, right there in red. And let me clean that up. It's actually looks really bad. So I'm going to think as I get close from the left side, let's look at the left side. As we get close from the left side, I'm trying to draw a highlighted arrow there. So as we're getting close from the left side, what's our output getting close to? So as I approach it from this left side, notice the output is getting close to 4. So what we have to do is just double check the right side real quick. You could see it as the same. So from the right side, as we're approaching it from the right side, from right to left, it's also getting close to 4. So this limit equals 4. We'll take a look at another graph. This one's saying what is the limit as x approaches -1? So the limit as x approaches -1 of h of x in this case. So -1 is right here. This time h is actually defined there, just the points up here. But remember, f of -1, because this is when x is -1, f of -1 is 4. But we don't care about what the function equals in regards to limits. We care about what it is approaching. If you don't understand me, rewind it and rewatch that. So what is it approaching? Let's look at it. Well, from the left, what are we approaching? So what's my graph getting close to? As x gets close to -1, the graph is approaching -3. So I'm going to put -3 for now. Let's just double check the right side. As we approach it from the right side, Well, guess what? Yes, it's also approaching, the output value is approaching -3. That's how high or low the value is. That's the output. It's also approaching -3. So from both the left and the right, we're approaching -3. Therefore, the limit equals -3. Now, the function itself, as I said earlier, the function at -1 is actually equivalent to 4 because that's where the point has been placed. This graph idea, this is really important for you guys to get down because as we get into the tables, it's going to make a little more sense if you can visualize the graphs as we go through the tables. So let's go ahead and take a look at the tables. It looks like we got a great graph here to go over. So what's a reasonable estimate for as x approaches -6? So as x is approaching -6, well, where would that be located? That would be located right here. Notice this is -6.1. If you think of the number line, -6.1 is over here, -6 would be there. So that's to the left of -6.1, and then over here, -5.9. Should have drawn it all the way across. -5.9 is on the right side of -6. So from the left and from the right, let's look at the table. So -6 would exist right here. So from the left, what's our output getting close to? Well, -0.25, -0.74, -0.98. Looks like it's getting pretty close to -1. I'm going to put -1 right there. We'll double check it. Let's look at the right side. As we get closer and closer, -5.9, -5.99, -5.999. As we get close to that -6, look at this, -2.3, -1.77. It's dropping -1.02. We're getting really close to -1. So I would say reasonably, we can assume that this is going to just, as we get closer and closer to -6 from the left, like if we had -6.0000001, it would probably be like -0.99999. You know, it's going to be a value really close to -1. So we can safely assume that this table, as we get close to -6, that it's equaling -1, that our function is getting closer and closer to -1. Doesn't mean that it actually equals -1, but we can assume it's getting really close to it from both sides. Remember, if it doesn't work from both sides, if it's approaching different numbers from both sides, we would say the limit does not exist. This one's just a vertical table. And this time they're saying as it approaches 1. So 1 would be located right here. So as we get close from the left, remember if you think of a number line here, 1.1, 0.9, 1 is right in between those two. So from the left is 0.9. 0.9 is from the left. So this is the left-hand limit. I'll put LHL. And then we do that in a different color. That's the left-hand limit. So as we get closer and closer to 1, what's our output getting close to? It looks like it's getting really close to -6. And you could already see, if we look at that right-hand limit, 1.1, as we're moving in from the right-hand limit, if you can tell, is actually also getting close to -6. So we could safely assume this limit as x approaches 1 is -6. Now, I don't like to assume in math, that in the graph we didn't have to assume. You could see it's visually, you could see it's getting close to it. But with tables, with numerical math, you do have to sometimes have some assumptions. So this is called numerical math. It's a representation. And so you do have to kind of do some assumptions and use your best mind. I mean, think about real life data is most of the time going to be put into a table. Think of Excel and things like that. And a lot of times in those, they're not going to be able to just create a nice formula and know for sure. We've got to kind of do some assumptions there. Let's look at this last example. What's the reasonable estimate for the limit as x approaches -4? And so I'm going to put a marking right at -4. That's right here. So from the left, it's approaching -4. -3. Look at that. So the left-hand limit, you can see, is -3. And we'll talk more about left-hand and right-hand limits. But if you look at, that's from the left. Just one more time, that's from the left. But if you look from the right, we're getting close to the value of 2. So the right-hand limit is 2. I don't like the using red there. I should have used a different color. So from the left, we got -3. Look at that. It's approaching -3. The output's approaching -3 from the left as we get close to -4. Remember, x is approaching -4 here. But from the right, as we approach -4, notice it's going up to 2. So this limit, we would say the limit does not exist. And that's an intro to limits. We're really going to dive in more depth of these very things we're looking at here, kind of bring in some new terms, new notation as well into this, and hopefully it'll make more and more sense.